Welcome to Session 13, Sampling Methods, Bias, and Representation. A statistical conclusion is only as trustworthy as the path that plays people into the sample. 10 examples distinguish simple random, systematic, and stratified samples from convenience and voluntary response, then diagnose wording, non-response, undercoverage, and sample size traps. Name the target population, trace who could enter the sample, identify who was omitted, and explain the likely direction of bias. Example 1. A university assigns every student a number and uses software to select 300 numbers. Identify the sampling method. The comparison places both cases on the same scale. Plan. Check whether every population member has an equal chance through random selection. Step 1. The sampling frame contains all enrolled students. Step 2. Software selects identifiers by chance. Step 3. No subgroup or fixed pattern controls selection. Step 4. This is a simple random sample. Quick check. A valid implementation must not omit students from the numbered list. This matters in real life because universities use random samples to estimate student needs without surveying the entire campus. Example 2. After choosing a random starting customer, a store surveys every 25th customer. Identify the method. The key quantities are organized before the arithmetic begins. Plan. Look for a random start followed by a fixed interval. Step 1. The first selected customer is determined randomly. Step 2. Afterward, selection follows every 25th arrival. Step 3. The constant step creates a systematic pattern. Step 4. This is systematic sampling. Quick check. A periodic customer pattern matching the interval could introduce bias and should be considered. This matters in real life because systematic samples are practical when customers or products arrive in a long sequence. Example 3. A company separates employees by department and randomly samples within every department. Identify the method and advantage. The comparison places both cases on the same scale. Plan. Recognize population subgroups sampled separately. Step 1. Departments form relevant subgroups or strata. Step 2. Random selection occurs within each stratum. Step 3. Then the method is stratified random sampling. Step 4. It ensures small and large departments are represented according to the design. Quick check. The final estimate should use appropriate subgroup weights if sampling fractions differ. This matters in real life because organizations use stratification when experiences may differ across roles or locations. Example 4. A reporter asks the first 40 people leaving a gym whether residents exercise enough. Identify the likely bias. The comparison places both cases on the same scale. Plan. Compare the convenient location with the target population. Step 1. The target appears to be all residents. Step 2. Only people currently using a gym can enter the sample. Step 3. Gym users may exercise more than other residents. Step 4. This convenient sample likely overestimates exercise levels. Quick check. A larger sample at the same gym would not fix the undercoverage of non-gym users. This matters in real life because health policies need representative community data rather than responses from an unusually active location. Example 5. A news website asks readers to click yes or no on a controversial issue. Explain voluntary response bias. The comparison places both cases on the same scale. Plan. Identify who chooses to participate and whose motivation may be strongest. Step 1. Website readers decide for themselves whether to respond. Step 2. People with strong opinions may be more motivated to click. Step 3. Casual or neutral readers may remain silent. Step 4. The voluntary responses may overrepresent extreme views. Quick check. A large click total does not make self-selected responses representative of the wider public. This matters in real life because media polls are engagement tools unless selection and population coverage are carefully designed. Example 6. A survey asks, should the city continue its wasteful parking program? Identify and repair the wording problem. The comparison places both cases on the same scale. Plan. Look for emotionally loaded language that pushes respondents toward one answer. Step 1. The word wasteful presents a negative judgment before the response. Step 2. That wording can influence answers. Step 3. A neutral revision is, do you support or oppose continuing the city parking program? Step 4. The revision allows the respondent to supply the judgment. Quick check. A fair question describes the policy without signaling the preferred answer. This matters in real life because public agencies need neutral wording to measure opinion rather than create it. Example 7. A random survey is emailed to 2,000 employees, but only 180 respond. What concern remains? The key quantities are organized before the arithmetic begins. Plan. Distinguish random invitation from the pattern of actual responses. Step 1. The invitations may have been selected randomly. Step 2. However, 1,820 invited employees did not respond. Step 3. Responders may differ systematically from non-responders. Step 4. Non-response bias could weaken the final estimate. Quick check. The response rate is 180 divided by 2,000 equals 9%, which is low enough to require investigation. This matters in real life because employers use reminders and multiple contact methods to reduce non-response. Example 8. A town triples a biased roadside survey from 300 to 900 drivers at the same morning location. Does the larger sample remove bias? The comparison places both cases on the same scale. Plan. Separate random sampling variation from systematic selection bias. Step 1. More responses can reduce chance-to-chance variation. Step 2. The location and morning time still exclude many travel patterns. Step 3. The same undercoverage remains in all 900 responses. Step 4. The larger sample is more precise about the wrong slice of the population, not necessarily more accurate for the town. Quick check. Sample size cannot compensate for a method that systematically omits relevant groups. This matters in real life because traffic planning requires coverage across locations, days, and times. Example 9. A school is 60% day students and 40% evening students. Design a proportional stratified sample of 200. The comparison places both cases on the same scale. Plan. Multiply each population share by the desired sample size. Step 1. Day students. 0.60 times 200 equals 120. Step 2. Evening students. 0.40 times 200 equals 80. Step 3. Randomly select 120 day and 80 evening students within their groups. Step 4. The two stratum samples total 200 and preserve the 60/40 balance. Quick check. The allocations 120 divided by 280 divided by 200 reproduce the population percentages. This matters in real life because proportional stratification ensures schedules and services reflect both student populations. Example 10. A hospital wants patient satisfaction data but excludes patients who do not speak English. Identify the coverage issue. The comparison places both cases on the same scale. Plan. Compare the target patient population with those allowed into the sampling frame. Step 1. The target is all hospital patients. Step 2. Non-English speaking patients cannot enter the survey as designed. Step 3. Their experiences may differ from English-speaking patients' experiences. Step 4. This is undercoverage and may bias the satisfaction estimate. Quick check. Translated surveys or trained interpreters would broaden coverage. This matters in real life because inclusive health research is necessary for equitable service improvement. Session 13 Recap. Random selection protects representation, while convenience, voluntary response, non-response, and undercoverage can systematically distort results. A larger sample reduces random variation, but cannot repair a biased method. Stratified sampling protects important subgroups when selection occurs randomly within every stratum. Quick check. A school randomly samples within every grade level. What sampling method is used? The grade levels are strata, so the method is stratified random sampling.